Revolution, the inner the time. Paradise is the inner the time. Everybody me say watching the time.
What a world, what a place to be. So many people in misery. So much pain, so much poverty. We all should be free.
Because this is a boss.
See the beauty is everywhere. On the earth we must take the care. We live in a paradise. We must treat her right.
Here we go.
Love is the answer.
Hear me say,
Paradise. Revolution.
it's revolution in paradise. Here we go. Hear me say.
Three-dimensional rapid prototyping models have become absolutely essential for everything from, say, routine jaw alignments right up to incredibly complex post-traumatic facial reconstructions. But the widespread clinical adoption of these 3D models, well, it's been severely bottlenecked by extreme costs. Today, we're looking at a fascinating, radical, and incredibly low-cost alternative, paper-based rapid prototyping. We're going to dive into the data to see if a model made out of standard everyday's office paper can actually meet the uncompromising demands of a highly delicate surgical environment. To figure this out, we'll quickly work our way through 5 areas: current limitations, the mechanics of paper-based 3D printing, dimensional accuracy, sterilization and cytotoxicity protocols, and finally, clinical application. All right, kicking things off with phase 1, current prototyping limitations. So, traditional 3D printers used in medical settings almost universally rely on light-cured resin. The problem? That resin is incredibly expensive, which makes large-scale production financially out of reach for a lot of hospitals. On top of that, finishing these resin models often requires really toxic chemical baths, and the resulting plastic isn't biodegradable at all. Paper-based prototyping, on the other hand, presents an amazing contrast. It offers a tiny fraction of the material cost, and it's completely biodegradable. But the real question we have to ask is, can standard paper truly replace specialized medical resin? Let's look at how it works in phase 2, paper-based 3D printing. The Matrix 300 apparatus from MakeCore Technologies is genuinely mind-blowing because, get this, unlike high-end medical printers, this machine wasn't originally designed for medicine at all. It was actually designed for architecture. It utilizes standard 80-gram A4 paper, literally the exact same sheets you'd use to print out a grocery list, bound together using a simple water-soluble adhesive. Yet, despite using everyday materials, it achieves a remarkably precise printing resolution of 0.01 millimeters. No way, right? The manufacturing process itself is just fascinating. First, a clinical 3D file of the jaw is imported. The software cuts the virtual model into layers that are exactly 0.1 millimeters thick, perfectly matching the thickness of a single sheet of A4 paper. A blade then cuts the shape layer by layer, bonding them with the adhesive. The final step is manual weeding. Now, using pliers to physically pull away excess paper from complex structures like teeth does take some time, but this wonderfully low-tech handwork completely bypasses those toxic chemical baths required by traditional resin models. And the physical output, once that weeding is complete, is staggering, especially when you look at the economics. To produce a complete model of a human lower jaw, you only need about 200 sheets of paper. Since a standard 500-sheet ream costs just a few bucks, the material cost to build this incredibly complex anatomical model is literally mere fractions of a euro. It's a total game changer. Moving on to phase 3, dimensional accuracy assessment. Of course, a cheap model is absolutely useless in the operating theater if it isn't accurate. And researchers didn't just eyeball this. To test the spatial precision of the paper model against a real human jawbone, they calculated exactly 2,850 discrete distances. They used a highly precise 3D measuring arm and mapped each point 20 separate times to guarantee exhaustive spatial validation. So, what did the data show? The results of that spatial assessment confirmed something incredible. Paper-based models have accuracy comparable to other currently used in maxillofacial surgery methods of rapid prototyping, specifically polyjet. Since polyjet printing is a widely accepted gold standard for maxillofacial interventions, this means our humble paper model genuinely meets the rigorous, high-fidelity dimensional requirements needed for delicate facial surgery. Which brings us to phase 4, sterilization and cytotoxicity protocols. Listen, accuracy is really only half the battle. A model might be dimensionally perfect, but if it causes an infection, it can never enter the surgical environment. This brings us to cytotoxicity, which essentially asks one crucial question: does this material kill human cells? And initially, well, the answer was yes. Tests revealed that raw, uncoated paper models exhibit unacceptably high cytotoxicity, making them strictly unsafe for the operating room. But here is the massive turning point. By applying a coating of 2-octyl cyanoacrylate, specifically Dermabond tissue adhesive, researchers drastically improved the material's biological behavior. The cyanoacrylate coating significantly reduced cytotoxicity of the models. It transformed an unsafe block of paper into a highly biocompatible surgical tool. The takeaway here? Paper models are biocompatible, unlike models made of light-cured resin, as long as they have this simple protective coating. With the biological hurdle completely cleared, the data confirms it is possible to use any classical method of sterilization on paper-based models. Importantly, their shape and structural integrity are perfectly maintained after being sterilized. The only minor catch is with gas plasma sterilization, which takes just a bit longer because the paper naturally absorbs hydrogen superoxide, necessitating some timing adjustments for larger prints. But fundamentally, classical sterilization works flawlessly.
Okay, finally, phase 5, clinical application in surgery.
So what are we actually left with here? This completed model is no longer just paper and water-soluble adhesive. Because of that cyanoacrylate coating, it is a fully biocompatible surgical model. It has successfully passed the rigorous spatial validation, it perfectly mimics human bone, and it's conquered the biological safety tests. The validated parameters authorizing this ultra-low-cost alternative are crystal clear. Biocompatibility is confirmed thanks to the cyanoacrylate coating. It perfectly tolerates classical operating theater sterilization without losing its shape, and its dimensional accuracy firmly aligns with the PolyJet gold standard. This brings us to an absolutely amazing conclusion. Based on the empirical data, there is a confirmed possibility of safe use in the operating theater as a template for the maxilla and the mandible. Just think about that for a second. We're taking everyday 80-gram A4 paper, a bit of glue, and rigorously proving its clinical readiness for some of the most intricate and delicate surgical environments in all of medicine. I want to leave you with this incredibly powerful confirmation from the study regarding its specific clinical utility. The paper-based model is very good for pre-bending plates as well, and acceptable as an intraoperative template. By removing the enormous economic barriers without sacrificing a millimeter of precision or safety, could standard office paper literally be the key to democratizing complex reconstructive surgery worldwide? It's a fascinating question. Thank you for joining me on The Explainer.